Good morning. This video is part 2 on section 5.1 on mid-segments. If you followed along in the first video, you should already have your guided notes that will help you along with this. So this is just moving on to the next slide. This set of slides in this video is going to focus on some different aspects of the mid-segment theorem that was studied in the last video. Here we're going to look at some different types of proofs and other types of problems that you can use the mid-segment theorem for. This example is a proof. It's a triangle proof that's going to be using the mid-segment theorem. We're given that ST, TU, and SU are all mid-segments of PQR. Remember, a mid-segment has two special characteristics. Number one, it's going to end up bisecting each of these segments into equal parts. Therefore, SQ and PS are equal, PT and TR are equal, RU and UQ end up being equal to each other. The second important piece is the mid-segment theorem, and that says two separate things. The first thing it says is that any mid-segment is going to be half the length of the non-adjacent side of the triangle. Therefore, in this case, SU will be half the length of PR. Likewise, ST is half of QR, and finally, UT ends up being half of QP. The last important piece of the mid-segment theorem states that it will also be parallel. So those same segments that I just mentioned, like SU and PR, not only is SU half of PR, but SU is parallel to PR. That employs a lot of interesting tactics that we can use our parallel postulates and parallel theorems that we learned in Chapter 3, like alternate interior, alternate exterior, corresponding, and same side interior. In this proof, I'm looking to prove that triangle PST, so I'll highlight this in purple here, so that this triangle here is congruent to triangle SQU. Again, in order to prove congruence, you either need to go the long route where you prove all three angles and all three sides are congruent, or you can use one of the congruence postulates like side angle side, side side side, and so forth. One of the tactics and one of the strategies that I see when I read this is because I know I have the parallel properties, I know that I can prove some angles to be congruent. For example, SU and PR right here tell me this angle right here, QSU, and SPT, I know they're going to be congruent because they're corresponding angles. Likewise, I know that S is bisecting QP. Therefore, SQ and SP will be equal to each other. So based on what I've read thus far, on what I've talked about, I know a side of SQU and a side of PST correspond, and I also know an angle QSU and SPT, they're also congruent because they're corresponding. So that's side and angle. If I have side and angle, the only other option I have in terms of a congruence postulate that I can use is side angle side. So if I can somehow prove that SU is congruent to PT, I have a side angle side congruence postulate that I can use, thus proving these triangles to be true. We'll talk about that particular one in just a moment, but let's begin our proof here. So we have our statement and our reasons, two-column proof. First thing I want to state is that ST, TU, and SU are mid-segments, and that's through my given. Now, let's start with the first fact. The first fact is the easiest fact. I know that SQ is going to be congruent to SP. That's because that is the definition of midpoint. Remember, S is the midpoint of QSP because SU ends up being the mid-segment. So that's my first check that I can make here. The next statement I can say involves the corresponding angles. Now, in order for me to say corresponding angles are congruent, the first thing I need to do is make a parallel statement. The parallel statement that's going to help me with that is to say that segment SU is parallel to segment PR. And that's from our brand new mid-segment theorem. So mid-segment theorem would be the reason I use for that one. Now that I've said they're parallel, I can officially now give myself the permission to say QSU, that's an S, apologize for the writing error. QSU is congruent to SPT, and that is, as we've said before, is because they're corresponding angles, and that is a postulate. So we'll call it the corresponding angles postulate. The last piece here that I need to talk about is to show that SU is congruent to PT. Again, that'll give me the side angle side postulate, which thus proves the triangles. Remember the second part of the midsegment theorem. The second part of the midsegment theorem says that SU will be 1/2 of PR. So let's make that statement. So I know that 1/2 of PR is going to equal SU. And that's again through the mid-segment theorem. We also should know that because T is the midpoint of PR, that PT will be 1/2 of PR. Therefore, I can make that statement. So 1/2 of PR is also going to be congruent, and number 5 should also be a congruent symbol, is going to be 1/2 of PR is going to be equal to PT, and that's through the definition of midpoint. What I see is equation 5 and equation 6 both say 1/2 PR. Therefore, I can make another statement saying SU is congruent to PT. And that is by substitution. And that's my third check mark. Side, angle, side. Bada bing, I have the proof. PST, the triangle, is congruent to the triangle SQU, and that is through our side, angle, side, and that completes this proof. In this next problem, I've already graphed my 3 points, as you can see at the right here, but read the problem here. Given the triangle with the endpoints of 3, 2, 7, 5, and 3, 7, find the length of the midsegment parallel to side AB. So the midsegment is going to be approximately somewhere around here. I'll use the pink highlighter to kind of approximate where I think that may be. So this pink line is the midsegment, and I know these two are parallel. I want me to find the length of the midsegment. Based on the midsegment theorem, I know that there's a special relationship between the length of this pink midsegment and the length of AB. This length will be 1/2 of the non-adjacent side, AB. So if I were to find the length of AB, I just need to cut that answer in half, and I have my length of my midsegment. Fortunately, because I have the fortunately I have the endpoints of AB, I can use the distance formula to find the distance between those 2 points. So the distance formula, again, for recap, is going to be your change in x's squared, and the change in your y's also squared. So in this case, in my problem, I will have 7 minus 3 squared. I will have 5 minus 2 squared. And from here, we just simplify. 7 minus 3 is 4. 4 squared is 16. 5 minus 2 is 3. 3 squared is 9. 16 plus 9 just so happens to be a pretty nice even number you should be happy to see. 25. Because the square root of 25 is 5. So 5 is the length of AB. Based on the midsegment theorem, I know that if the length of the side AB is 5, the length of the midsegment parallel to side AB, aka this pink line, was half of that. So the midsegment will have a length of 2.5, half of that. This last problem in your notes says to use a coordinate proof. We'll talk more about coordinate proofs when I return. So for this basic problem, we have enough information here that we don't need to do a formal proof. Basically, you're going to be given this information, and I want you to show me that WV is parallel to OH, meaning they have the same slope, and WV is equal to 1/2 of OH, which we'll find through distance. To begin this, we got to find the coordinates of W and V. We know WV is a midsegment, meaning W is the midpoint of O and G. If we have the endpoints of this segment, we can use the midpoint formula. to find the coordinate for W and the coordinate for V. The midpoint formula, as we recall from the beginning of this course, is just the average of the x values and the average of the y values. So our coordinate for W here is going to be the average of 0 and 6. 0 plus 6 is 6, and that divided by 2 is going to be 3. Same thing goes for y. 0 plus 6 is 6, divided by 2 is 3. Point W has a coordinate of 3, 3. As we go over to V, the average of 6 and 8. 6 plus 8 is 14, and 14 divided by 2 is 7. And finally, 6 plus 0 is 6. 6 divided by 2 is 3. So 3, 3 and 7, 3. In order to prove the parallel portion of this, I need to show the slopes are equal. Fortunately, since they both have the same y value, my slope of WV ends up being 3 minus 3 over 7 minus 3, which gives me 0 over 4, or 0. So WV has a slope of 0. As for the bottom, same thing goes. 0 minus 0, take a look, we'll have another 0 up top, 8 minus 0. So I have 0 over 8, which will be 0. So OH has a slope of 0. So these are indeed parallel. Finally, in order to show that WV is 1/2 of OH, I need to find the distance. Normally this would be used for the distance formula, but because this is a horizontal line, WV and OH are both horizontal, I can just simply count the distance or the change in x. So 7 from 3 gives me a length of 4. WV will have a length of 4. OH is going to have a length of 8 and 0. So the difference of 8 and 0 is 8. OH is 8. And that's going to prove my other portion here, that WV is 1/2 of OH. This will conclude the second video on 5.1 on mid-segments. At this point, please return to the Google Doc to take a look at the assignments that I have set for you for the rest of class today. One of which is going to be this textbook assignment on page 298 to 300. Complete the following problems that you have here. Thank you for watching.